very much for that introduction. I appreciate that. So I don't know about this distinguished speaker. My wife says distinguished just means I have more gray hair than I used to. So. But in the interest of trying to teach people something new, what I want to talk about is a topic that probably most of you have never really encountered before. So hopefully you'll come out of here learning something new. And then I want to talk a little more in depth about what some of my students and colleagues have been working on in this area. So it's important to point out that Peng Li was one of my PhD students. He really did the work here. Xin Li was a postdoc of mine who also did a lot of the work here. And Wei Kang was a PhD student with one of my colleagues. And the three of us take the credit while they did all the real work. You know how that works, right? So I want to talk about approximate computing and what this buys us and where we can go with this. So the opportunity here, what kind of motivated all this, was if you look at technologies that are coming up, deep submicron CMOS, spintronics, carbon nanotubes, pick your favorite new technology. There's some real opportunities here. We get very high densities, so we get a lot more bits. We get more transistors, therefore more logic. We get more interconnects, so we can do a lot more within a limited space. Or at least that's what people are trying to tell us who are developing these technologies. So I think these technologies are very interesting. I have no idea where they're going to go. But one thing I do know is that regardless of what technology we're going to use, we're going to see many more variations in these devices. We're going to see more timing variations. We're going to see more process variations. We're going to see higher defect rates. Ultimately, all this is going to lead to higher error rates. So we were looking at this and say, okay, is there something we can do here to try to tolerate this in a reasonable way and not tolerate it using conventional means? And I'll talk a little bit about what I mean there. Conventional assumption is that noise is bad, right? If I have a 0 and some alpha particle or something comes in and changes that 0 to a 1 or a 1 to that 0, then I get the wrong output and everybody's angry. Okay, nothing works, my bank balance is off, the world is bad. Our question was, can we somehow use this random noise to somehow compute reliably? Well, a hint is, since it's noise, reliable computing in this case will be probabilistically correct. So it'll be approximately correct. We can't guarantee an outcome, but we can at least get something that is pretty close to what we want. For some applications, this will work very well. For some applications, maybe not so much. So our strategy is to think of this approximate computing as computation on stochastic values or probabilistic values. So think of logic design as arithmetic operations on values between 0 and 1, where I have some probabilistic input, I have a very conventional digital circuit here, and then I have some probabilistic output. Right? This circuit is just AND gates, OR gates, muxes, so forth. There's nothing special in the circuit itself. The specialness comes in how we interpret the inputs and outputs. Okay? So let me give an example. This is kind of an image differencing example. It's a little bit more complex than that. I'll explain the details later. But the idea is that I essentially want to take the difference between two consecutive images and use that to separate the background from the foreground so I can see, aha, this is what was changing from one image to another. Okay. Here's my punchline. I've got that image, and I've simulated this over a number of different iterations with different inputs where I'm injecting errors into the circuit. So along the bottom here, I inject errors from 0%, no errors, to 1%, meaning that every node in that circuit has a 1% probability of changing from a 0 to a 1 or a 1 to a 0. So it's just a way of trying to simulate faults in the system. And I go out here to 30% errors injected, meaning 30% of the nodes in the circuit are computing the wrong thing. Right? And what I see is what you might expect. With no errors here, I get an image like this. Inject a little bit of error, I start to see this snowy pattern. And finally, when I'm at 30%, you can barely see what that image is. It's almost completely wiped out. Traditional approach for tolerating this would be something like triple modular redundancy. So I duplicate the circuit 3 times, I compare, and I take the best 2 out of 3 and say, okay, that's the correct result. If I do that, I see the same pattern developing here, but it's just shifted. So I can tolerate more errors. You know, here, this at the 5 or 10% errors looks similar to one back here at maybe 1 or 2% errors. So I've compensated for some of those errors. But I still have this problem at the end where things get all snowy and the image becomes unusable. And it's expensive. I had to triple the cost of the circuit plus a little bit of voting logic. So it's a very expensive solution. Our stochastic approach, on the other hand, we can go out to 30% errors here, and you really don't see hardly any difference. Okay? The thing to notice, what we paid, is that the original output here is a little bit different than the original output there. Okay? So this image, it's good enough for me to use, but it's not perfect. It's not exactly what I saw in the previous correct image. So if I can tolerate that change in the output, say it's approximately good, but it's not perfect, the benefit I get is this huge reliability improvement, where I can have a very, very large number of errors, and I still produce an output that's still pretty good. As one other example, here's something called gamma correction, which is a function to try to improve the quality of an image. And I can see 1%, 2%, 10% errors. I get this snow. With the stochastic implementation, things just kind of gracefully fade away. Okay? So if I can tolerate that failure and this graceful degradation, then I can tolerate a lot of failures using this architecture. Okay? That's the advantage. That's my punchline. So with that, I'll take any questions and we can go on. No. Now, we're not the first one to think about probabilistics in designing circuits. If you go back to Shannon, he looked at probabilistic signals. You have the source of a transmitter. You have a receiver. You get some noise injected, and the goal is to try to separate that signal from that noise. Okay? People look at probabilistic analysis in digital circuits. So I have some probabilistic input. This is generated. This is something you generate automatically. I have this circuit. I designed it, so I know what it is. And then I generate or capture the output from this generated input, and I use this for like signature analysis to test circuits, for instance. What we're proposing is probabilistic synthesis. So I've got these same probabilistic inputs and outputs. The difference is that I give you the inputs. This is what we want. I give you the outputs. This is what I want to happen when you give me that input. And what I want you to do, or what I want to do, is to design that circuit in the middle. So given the inputs, given the outputs, how do I design a circuit that has those nice characteristics that I showed you before? All right. Well, the way we're going to do this, we're going to think about these inputs and outputs as probability values. So the inputs are numbers between 0 and 1. The outputs are numbers between 0 and 1. Okay, but this is just a combinational circuit. It's just ands, ors, muxes, and so forth. So what I'm really thinking of is streams of bits coming in here. So think about each one of these as one clock cycle. On the first clock, my input is 0, 0, 1, 1. My output is 1, 1 here. Then I increment the clock, and my input is now 1, 1, 0, 1, and so forth. So I'm encoding these values, 4/8, for instance, using this bit stream so that over time, over some arbitrary period of time, on average, 4 out of 8 of those bits, or 50% of those bits, are a 1. I don't care what order they're in. I just say over this period of time, half of them are going to be a 1. For this one, I'm trying to represent 0.8 or 0.9. So 80 or 90% of the time, those bits should be a 1. Okay? That's my representation. Instead of a conventional positional notation that you're used to, binary 2 to the m type notation, I'm just going to have every bit equal the same value. And I'll just stream a bunch of those together. All right? So mathematically, what I'm really thinking of is that for each one of these bits, the probability of that bit at any given time being a 1 is x, where x is the value that I'm trying to represent. And that gives me real values between 0 and 1 that I can encode using this format. We call that a unipolar format. I can also scale it by adding 1 dividing by 2, and I can represent values between -1 and 1. It's exactly the same thing. I just think of it as between 0 and 1 or between -1 and 1. It doesn't matter. These are interchangeable representations. Some cases it's easier to think about plus and minus 1. Some cases it's easier to think about 0 and 1. But I can actually mix and match them in the same circuit, and it still works fine. Okay. Yeah?
The different inputs, I assume they are independent? Or?
They have to be independent. Yeah, and I'll get to that point again later. Yes, if they're not independent, bad things happen. All right, so that's my representation. Here's one of the key benefits, this fault tolerance that I demonstrated earlier. So if I think about a conventional approach where I have a binary radix encoding, here I have the value 7/8, 2/8. Some alpha particle comes in and flips that bit from a 0 to a 1. What happens? Well, the input changes from 2/8 to 6/8. I change that most significant bit, and I see a big change in the output. Okay? If I would have changed the least significant bit, I'd see a small change in the value of the output. But I don't know where that error is going to occur. It's going to happen somewhere. So if I'm out of luck, if I have bad luck, then the most significant bits are going to be changed, and I'll see a big change in the output. That's why we saw that snowy image when we started to introduce errors in that previous circuit. So this stochastic encoding, I have this stream of bits flowing, and if I zap any one of those bits, it changes from a 0 to a 1. The worst that can happen is if I've got 8 bits representing this, is that I have an error of 1 out of 8. If I have 100 bits representing this, the worst that happens is an error of 1 out of 100. 1,000 bits, it's 1 out of 1,000. Okay? So the more bits I have, the less the impact of the error, but it doesn't matter where the error occurs. Okay? It's always going to be 1 out of 1,000 if I have 1,000 bits. So that's one of the key benefits. We have this fault tolerance. Another benefit is that arithmetic is really, really cheap. Okay? If I think about these streams of bits coming in here, I have a stream of bits coming in A, a stream of bits coming in B, and I'm performing the AND of those. Mathematically, I'm saying the probability of C being a 1 is the probability of A being a 1 and the probability of B being a 1. If I just convert that to a mathematical description, then this C, fractional value, is just the product of A and B. So I've now got a multiplier made up of an AND gate. Okay, this is extremely inexpensive arithmetic. One AND gate to do a complete multiplication. Okay, I've paid for it in time because I've got these long streams of bits coming in, but it's very cheap to implement. Addition actually turns out to be just slightly more complicated than multiplication. If I have this multiplexer, the selector input chooses between A and B, so the probability of being a 1 on the output C is the probability of this being a 1 and that being a 1, or the probability of this being a 1 and that being a 1. So I've just done a scaled addition where I have the selector times the probability of the input on A times 1 minus the select value times the probability of being a 1 on the input of B. All right, so I've got multiplication and addition, very cheap. What's a multiplier? One AND gate. What's a multiplexor? Well, it's 2 AND gates and an OR gate. So it's very cheap to do arithmetic here. Okay? This is the good thing. How do I use this? How do I generate some interesting functions out of this? Well, I think about it as a functional circuit where I have some stream coming in, t, that's the input value between 0 and 1 or between -1 and 1. And I have some function that I'm trying to compute on that. And what I want to do is design that combinational circuit in the middle. All right? So the question is, what kind of functions can I implement with this circuit? What possibilities do I have? And given the description of the input and the output, how can I synthesize this? How can I automate this process so you don't have to sit down and think? You just say, here's the input and the output. Here's a CAD tool that will do that for you automatically. All right, well, it turns out that with combinational circuits, I can implement polynomials. They have to be polynomials that map from the interval 0, 1 to the interval 0, 1. But I can do pretty much any polynomial I want. I'll talk a little bit later about how to make that into more complex functions, non-polynomial functions. But we'll look at the polynomials first. All right. Take a sidestep here. Think about what you do with Fourier transforms. I have a time-varying signal, and I represent that as a linear combination of basis functions, sines and cosines, or this complex exponential. All right? So you've all seen this before. I can take my function, represent it as a sum of these Fourier coefficients and this basis function here. Right? This basis function works very well if I have periodic signals. right? If I have something like polynomials, what do? Just choose a different basis function. Okay? If I do Taylor series approximations, for instance, I choose one basis function. If I want to do different type of approximation, I can choose a different basis function. It doesn't really matter what basis function you use from a mathematical point of view, but from an implementation point of view, turns out this thing called a Bernstein basis function has some very nice properties for this probabilistic problem that I'm talking about. Here what I do is represent my function as a linear combination of these Bernstein basis function polynomials. So I'm now reducing the problem to somehow trying to find these Bernstein coefficients. Okay? How many people have ever seen Bernstein basis functions before? Okay, and a small group over there. Most people look at this and say, I have absolutely no idea what you're talking about. But that's okay. What I want you to get out of this is that it's really just another form of expansion of a function. But I like this particular basis function. Why? Well, if I look at my multiplexer, look at the basis function from the Bernstein polynomial, and I look at the operation that this is performing, immediately see, aha, this looks a lot like a linear combination of these Bernstein polynomials, these Bernstein basis functions. So if I can find a way to write my function as a linear combination of these, then I should be able to use this multiplexer to implement that function and automate this entire process. All right? So how do we do this? Well, if you just start with something like a Taylor series expansion of my function g of t, remember that's the output that I'm trying to produce. Then I have this Taylor expansion. I can go out to whatever degree I want to get whatever level of approximation I want. And then I just have to find these Bernstein coefficients. And it turns out I can just solve them using this formula. It's just mildly complex, but it's easy to automate that. So now I've got a way to take this original function, come up with these Bernstein coefficients, and voila, I can implement this function in this Bernstein notation. All right? Now, obviously, I've skipped a step or two between here and here. And if you're interested in the math, we can talk about it later. There's some interesting properties or interesting things I have to do to make sure these coefficients all remain between 0 and 1. But I can prove that by elevating the degree of this polynomial, I can eventually make sure all these coefficients are between 0 and 1. And it turns out that for normal polynomials, I don't need to go beyond a degree of 3 or 4 in order to make this work. And the degree is important because that determines the cost of the implementation. All right? So this is what the circuit looks like when I'm done. I have the summation where I have n copies of the input t. And this gets to your question of, do the inputs need to be independent? Yes. If I need more than one copy of the input, then I have to have an independent copy of that input. So here I need n independent copies of the input t. And then I put my Bernstein coefficients in here, and the output is just that Bernstein polynomial. And I've chosen these coefficients to approximate whatever polynomial that I'm interested in. All right? So as an example, before I do that, let me point out the nice thing about this from a hardware designer's point of view is that this is very reconfigurable. All I have to do is put in new coefficients, and this exact same hardware can compute a completely different function. Okay? So as an example, here's the polynomial that I want to implement. F of t, 1 over 4, 9 over 8, blah, blah, blah. Okay? I go through my conversion to a Bernstein polynomial, and I end up with this polynomial. Excuse me. Notice all the coefficients are between 0 and 1. The other thing to notice is that here I had a degree 3 polynomial. Here I also have a degree 3 polynomial, but I've got more terms in here. So it expands a little bit in the process, but that's okay. I can live with that. Now when I put this into the circuit, this is all I have. I've got this simple adder here, and I've got this multiplexer, and I claim that this now implements that function. So down here, the input to the multiplexer are my Bernstein coefficients. You can see here. The input t is right here, and I need 3 copies of that because I have 4 copies, or sorry, 4 coefficients that I have to select here. So I have to have enough copies of the input to be able to select all 4 of those. The output is produced here. And then I just look and see how it steps through cycle by cycle. So here's my input value. All of these are representing 4/8, but just randomly I got 0, 0, 1 for the first cycle. On the next cycle, this is not truly an adder. It's really just counting the number of ones that are coming into it. So I have 1, 1. That means I have a 1 coming out of here. That means I select that multiplexer input. So I select that 0, and that propagates through to the output. Okay? So all those other values I'm just ignoring because I'm just randomly selecting these, but I'm selecting them weighted by these different coefficient values. Okay? So next cycle, I go here and I have 2 of these inputs are a 1. I select this second multiplexer input, and that gives me my output there. So I just step through that each cycle, and on average, the output will be, in this case, the value of 4/8, which is the functional value when I have an input of 0.5. Okay? So that's how the circuit works.
So how many bits you picked x1, x2, x3 to represent 4/8?
Right. So how many bits do I need in time here?
Yeah, to represent your input.
Right.
4/8. Is that?
So here I just show what 8 bits represented there, just because it was an easy example. In practice, I want probably hundreds, maybe 1,000 bits to represent that.
To get the accuracy.
Right, and I'll show a little bit later how much accuracy you get for different numbers of inputs, different levels of the representation. Okay, and that's one of the key weaknesses here, is how many bits do I need to do this? It turns out that it doesn't matter if I do this replication in time or if I do it in space. I can do all of these bits in parallel and just pay more hardware to do that. So I can reduce the latency as far as I want just by paying for more hardware to do that. But we'll see some of the trade-offs here.
So then if you pay for more hardware, then how does it compare with conventional?
Yeah, very good question. And I'll get to some results later with some of those comparisons. All right, right now I just want you to get the general sense of how this is working. All right. So the general process, here's my target function. I generate the Bernstein polynomial. And if I have something that's not a polynomial, then I could do some sort of least squares minimization and find the coefficients that do the best fit for whatever level of fit that I want. For example, that's what I did with this gamma correction. Gamma correction is just t to some constant value here. In this case, I ended up with, what is this, a degree 7 or degree 6 polynomial to implement that. And that's how we were able to generate these examples. Okay? So I can do some non-polynomial functions here if I'm willing to do that least squares approximation. But there are some kinds of things that just don't work very well. If I have periodic signals, if I have inputs or functions that have very sharp transitions, transcendental functions, exponentiation, absolute value, thresholding kinds of functions, those don't work very well with that Bernstein implementation. To get an accurate fit, I need coefficients out to 12, 13 degrees. So what else can you do? Well, we started to look at finite state machines. So think of a finite state machine here. In this case, I have n states, and I have one input. This input x just is a stream of bits that come into this finite state machine. And if x is a 0, I go left. If x is a 1, I go right. And then when I get to the ends, it's just a saturating counter. So if x stays in a 1, I stay at the end. Go to the left. If x stays a 0, then I just stay in that state. So think about this as this input stream comes in. I'm just moving back and forth across these states. Right? I can analyze this as a Markov chain. If I just draw a line in between a couple of states, I know that the flow to the left is equal to the flow to the right, so I can do a normal Markov type of analysis. I know that I have to be in one of those states, so the sum of those states has to be a 1. And then I find that the probability of being in any state I gives me this function. Okay? So now my basis function is this p of x over 1 minus p of x. where P of x is the probability of the input stream. So this, the probability of any one of those bits being a 1. So I now have this stationary distribution for this finite state machine. Okay, given this stationary distribution, I can now come up with a variety of different functions simply by choosing which of the states I decide to select when they're 1. Set some of those states to 1, some of those states to 0. If they're 1, that's my output. Right. So the implementation is pretty straightforward. Here's my finite state machine. It's just made up of registers, flip-flops, nothing unique. I have the input x. I have some logic gates here that just pick out certain states here, or them together, and then that produces this function y equals f of x. So the question is, how do I come up with these functions? How do I come up with these logic gates? How do I decide which states to set to 1 in order to implement the function that I want to implement? And what can I implement? Right? Well, here's an example. If I make, for every state to the left of the middle, if I make the even states 1, so the output is set to 1 if the state is even, and on the right-hand side, if the state is odd, I make the output a 1. Okay? If I do that, I can go through some analysis, and I can show you that this actually produces an absolute value function. Right? So the ideal function is this sort of gray line in the middle, and then these other lines show the approximation I get with a different number of states. So if I use an 8-state approximation, I get this yellow line, which is pretty close, but not perfect. By the time I get up to 64 states, my approximation is just right on top of the ideal function. So absolute value, very simple to implement. Okay. I can do exponentiation of absolute value. So e to the minus 2g square root, or absolute value of x. G is a selectable parameter. It's how far from the middle I set those states to be equal to 1. So if g is very large, I have a very large range where the outputs are 1, and then the ends are 0, or I can have a smaller range. That parameter g turns out to have some impact on the noise that this circuit generates. But for now, just think of it as a constant. Right? If I do that, the ideal version of this function is this gray line, peaks in the middle. If I have an 8-state implementation, I get this yellow line, 16 states, 32, 64 states. So with a 64-state machine, I get a pretty good approximation of this relatively complex function. Right? I have to do an exponentiation, take an absolute value. If I tried to implement that in conventional logic, that would be a very expensive thing to do, ideally. In my case, we're just going to say, well, let's approximate it. We'll get pretty close, but we're not going to be perfect. And we can do a very complex function with very simple hardware. All right? Here's a limitation. So that 32-state machine implementation, here's a target function in red that I'm trying to implement. With 32 states, with that linear state machine, this is as close as I can get. So some functions are just hard to match with that. The problem is that I've got 1 degree of freedom. I've got 1 input, and I can move left or right. So what do you do in order to give yourself more flexibility? You create another degree of freedom. So now I can have a 2-dimensional state machine. So now I have 2 inputs, x and k. So the x input will move me left and right. The k input will move me up and down. Okay, so now I've introduced another degree of freedom, and the goal is hopefully I can now approximate these functions more closely with hopefully fewer states. Right? Well, in fact, I can't. Here's that function that I was trying to approximate with a 32-state linear machine, and I couldn't get very close. Here, with 4 states in the 2-dimensional version, I'm right on top of it. So think about that. 4 states, a 4-state state machine is 2 flip-flops. So with 2 flip-flops and a few other logic gates, I can implement this kind of function almost perfectly. And I can do lots and lots of functions very, very close with just a couple of states, just a very small state machine. All right. So how do I synthesize things in general from this? Well, this is what the circuit looks like. If you think back to that generalized multiplexer that I showed you with the inputs, the adder, and the multiplexer, this is the equivalent circuit for the finite state machine, where I have this two-dimensional finite state machine here, which remember is just registers and some logic. I have two inputs, x and k, where k is a parameter that I choose as the designer. I have m bits coming out for the state. And then I have this multiplexer, and I'm going to select these different coefficients based on what state I'm in. So it's very much like this Bernstein implementation. In this case, my problem is to choose k and these coefficients so that this function, my output, is as close to the f of x as I want it to be. Okay? So I can have more states, more coefficients, and I can get a better approximation of the function. If I'm willing to pay less for it, I can get a worse approximation for the function by having fewer states and then fewer coefficients here. All right? All right. Yeah, question?
So in the two-dimensional state machine model, how many rows and columns? I guess it's a related question.
Right.
Yeah.
So how many rows and columns here? As many as I want. Okay, so I can just choose an arbitrary number of states, and it doesn't have to be square. All if I make it square, it's a little bit easier to analyze. Okay. All right. How much does this cost?
So we are talking about the ALUs. Basically, the functions that we want to implement here are mathematical functions.
Yes.
But what about errors in the load store unit or reorder buffers? Because if there is an error there, then how are we going to have a probabilistic design for those kind of units?
So excellent question. The question is, how might you do a probabilistic design for register files, adders, branch predictors, things like that in the processor? And the answer is, I have absolutely no idea. We're not even going to look at that yet. What I'm looking at here is functions, problems where I can describe them as a function. So I'm thinking of streaming applications where I have frames of video coming in. And I want to do something with those frames of video, and I want to produce an output for that. And I've got this continuous output that I'm producing. If I'm thinking about a more conventional general purpose microprocessor, no, I'm not advocating this for that sort of design. No. Later, perhaps, but we're not there yet. Okay. Any other questions, as long as I paused here? Yes, sir.
Well, kind of along those lines, just to check my understanding I'm a little fuzzy on how we connect some of this with the picture example. For the picture example, do you then take your bit values, produce a lengthy stream that have probability, run it through the circuit, and on the other end, collect a lengthy thing and compute count the probability in a reliable circuit there? Or?
Right. And I'll show an example that kind of shows the entire flow of how that works with some image processing examples. But what you said is exactly correct.
Okay.
Okay. So how well does this work? We're going to look for our figure of merit as area delay product. So the idea behind area delay product is in a conventional implementation, say I've got a multiplier here, I've got m bits, multiply, and I produce m bits. I've got a critical path length, so that's the minimum delay through the circuit, that sets my clock rate. And then I have some latency number of clocks to get through that. So maybe 2 clocks, 3 clocks, 4 clocks in order to get through that circuit. So I multiply the area times critical path by the number of cycles, the latency, and I get this figure of merit area delay product. The idea behind this is that I could make it go faster by spending more hardware and make this multiplier bigger. Do it more of it in parallel, and I get a reduced time, but it costs me more. Okay, so this product says, what's that trade-off? You know, if the area of the multiplier grows by m squared and the delay reduces by m, then I'm going to see this grow faster than the performance that I get back out of it. Okay, so we're going to use that same figure of merit for this stochastic implementation, where in this case I have streams of bits coming in. So as before, I have some area for this. So that's the area of the circuit. How many gates does it take to implement that circuit? I've got some critical path delay through here. How fast can I clock this thing? Key difference now, though, is that I'm doing this in a bit serial fashion. So if I have m bits of resolution, so 2 to the m is the width of the multiplication over there, then it's going to be 2 to the m cycles to get through here. So if I'm doing a 10-bit resolution, 2 to the 10th is now suddenly 1,024 bits to get through there. So it's going to take a lot longer, but my hope is that the area of the stochastic implementation is going to be so much less than the area of the deterministic implementation that this product here is going to be smaller than the product there. So I'll have a win on this overall area delay product. It may take a little bit longer in latency, but it's so cheap to do that maybe I can tolerate that latency, especially given the fault-tolerant aspects of this. Right, so here's an example for some trigonometric functions that are used very commonly in DSP and other types of applications. I have sine, cosine, hyperbolic sine and cosine, and so forth. And for a deterministic implementation, I do a quartic implementation. For anybody who remembers computer arithmetic, quartic is a very cheap way to implement some very complex functions, and I do a little bit of iteration and I get the result pretty quickly. The key thing is that it's the cheapest that I can come up with for an implementation of these types of functions. And if I look at the stochastic implementation, area delay product for m equals 8 bits, I see that my stochastic implementation is smaller than any of these other 4. Okay? So it wins in this case. If I go up to 9 bits, I'm still less than any of the other implementations. By the time I get to 10 bits, then I'm better than a couple, but worse than a couple. So 10 bits for this implementation seems to be my threshold. If I need finer resolution than that, then the stochastic implementation is probably too expensive. Right. Now let's look at some, I want to say real examples, using some image processing examples. I'm going to look at edge detection, a median filter, contrast enhancement, and kernel density estimation. Edge detection, if this is my input, what this circuit does is find the edges in that image. Okay? It does this is a standard thing, this is nothing new that I've done, where you just compute this function for each pixel. So you'll look at these cross values, and then by running this across every pixel, you can find these edges. Okay. What this looks like in the stochastic domain is that I've got the pixel and these adjacent pixels. This multiplexer and this multiplexer are doing a subtraction. This finite state machine implementation here is doing an absolute value function, which I saw here. And then I'm summing these two together here to produce the output. So the way this works, to your question, is that for every pixel here, I somehow have this 10-bit value. I have to convert it to this stream of bits. Then I run it through here, and I have a stream of bits coming out here, and then I have to add those up. I just run them through an adder to figure out what the binary equivalent is there. Okay? That conversion at either end is kind of expensive. And we've been looking at some circuits recently where we can detect directly in a stochastic domain, basically using sigma delta converters. And I can do an analog to digital conversion from analog to stochastic and then back to an analog value here without doing this binary translation in the middle. We don't have that fully worked out yet, but we're close. We're confident that it will work. So for this example, just think about these values coming in and producing these values coming out the other end. So it's this continuous stream of images coming in. And in fact, we can duplicate that circuit as many times as we want and do all pixels in parallel. So I can have the delay to get through this entire circuit, just whatever the delay is to get through that stochastic circuit. Okay. The noise filter, I have a similar kind of thing. This is a median selector. The key operation here is this select here, where I have two inputs coming in. I send the min on the top and the maxima on the bottom. So it's a sorting network. Each one of these sorters looks something like this, where I have a subtractor, stochastic subtractor. I have this finite state machine to do the thresholding, and then I select one or the other stochastically with this multiplexer. So I have the pixels coming in, run through here, and I have the pixels going out through this sorter. Contrast enhancement is really just a scaling function. So I have a subtraction here. I've got a couple of constants coming in here based on this scaling that I want to do. So I have the pixels coming in, they get multiplied here, and different values coming out there. Okay. This one's a little bit more interesting. This is a kernel density estimate. This is the example that I showed earlier. It's actually a little bit more complicated than what I said previously. What I really do is take the current image and n images back, however many far back I want to go, and I compute this density estimator for each pixel, and then I do a thresholding operation to say, is that changed or not changed from this image back n images where I have an exponential decay across the n images back. The circuit looks like this. Here's the current image, xt. Here's all the other images back. In this case, I go 32 images back, 32 frames back in the sequence. And then I do this exponentiation operation through here, and I do some summing, and then coming out here is that thresholded value. So for each pixel of these 32 images, the sequence of 32 images, I run it through the circuit, and then I get this result coming out here. Okay? From a cost point of view, here's the difference for those 4 implementations compared to a conventional implementation. For the edge detector, this is all normalized to the stochastic implementation, the blue bar. The edge detector is about 7 times more hardware than the stochastic. The median filter is about 6 times. The contrast enhancement circuit is about 16.5 times more hardware. The KDE segmentation is 267 times more hardware than the conventional implementation, which makes sense. To implement exponentiation conventionally requires a lot of hardware. Here I do it just with those thresholding circuits and those stochastic adders, so I'm much, much cheaper here in the stochastic implementation. All right? If I look at this normalized area delay product, I don't look so good for these relatively simple circuits. And the problem there is that I've got this 2 to the m bit latency to get through there. For the more complex circuit, however, I'm about 4.5 times better in this area delay product, simply because the circuit is so cheap in the stochastic implementation. Now, the last question is this error tolerance question. Where do these errors come from? How tolerant are these circuits, these more complex circuits, to the errors? I showed you the examples at the beginning. Here's a little bit more detail. So on the horizontal axis here, I have the fraction of injected errors. So this is the percent of all nodes in the circuit where I flip from 0 to 1 or 1 to 0. And those are randomly selected on each cycle. On the output vertical axis here, that's the fraction of output bits in the final image that are wrong compared to the golden image, the correct output. And what I see is that the deterministic implementation, if I have no injected errors, I get no errors on the output. Makes sense. As I increase the injected errors, I suddenly hit this threshold where things really take off, and the number of errors in the output get bad very quickly, because I'm hitting a lot of most significant bits, and I'm getting a lot of big errors here. The stochastic implementation, it's basically constant. Okay? I have some level of error that's always existing in the circuit, but as I inject more errors, it doesn't really matter. And the reason is because the error injections are unbiased. It's as likely that I go from 0 to 1 as 1 to 0, so they tend to cancel each other out over time. I see that with all the circuits that I looked at. The errors for the stochastic implementation are basically constant. The other ones blow up very quickly. The reason for that, 3 reasons. One is the function approximation. As I said before, if I have more states, I get a better approximation. So if I have fewer states, my approximation of the function isn't so good. That's one source of errors. I have quantization error. This is your question. How many bits do I use to represent the value? The more bits I have, the better the representation is, the less error there is. If I have fewer bits, then I can compute faster, but I have more quantization error. And some of the specific functions, the quantization error is a function of some of those parameters I selected, But in all cases, it's just a function of 1 over the number of bits. More bits is better. And then the last reason for the error is just the inherent error in these random bit streams. So if I think about any stream of bits, if I'm repeating this over multiple computations, I've got a mean value. That's the value I'm trying to represent. But there's also variance associated with that. And that variance is a function of the inherent randomness of these bit streams. And that's a function of a square of the number of bits. So if I want to increase or reduce this random fluctuation, I've got to double the number of bits every time. So it's an expensive operation to reduce here. But again, the final conclusion is that the number of bits matters. The more bits is better. Right? So I want to leave you with thinking of this as one end of a spectrum. If you think about conventional notation, think of that as one end of the spectrum, where it's very compact and every bit position is very important. I can't screw up one of those without screwing up everything in the computation. At the other extreme is this stochastic encoding I've been talking about, where each bit has exactly the same effect on the output. It's 1 over L is its resolution. So I have these two extremes. One of the things we've been looking at recently is some encoding sort of in the middle, where I have some value of the binary. The binary implementation is nice because it's compact. I have very few bits to represent a large range of values, but it's very subject to these errors. So can I somehow get a mix of these two? And we've got a couple of things that look very promising here. We call it binary stochastic. The interesting thing about it is that I end up with non-unique representations of values. So the same value can be represented multiple ways, which is good for fault tolerance, but kind of weird when you're trying to compute things in circuits. All right? I also want to mention that we're not the first ones to look at these sort of probabilistic ideas. As I mentioned, Shannon looked at it from a communication point of view. Von Neumann back in the 50s actually looked at this idea of kind of circulating values to improve reliability of logic circuits. And then Brown and Card in particular did some work looking at these finite state machine constructs. They came up with a couple of empirical examples. And then my student came in and did some mathematical proofs of these and then some synthesis of this. Some people have looked at probabilistic gates, where the gate maybe computes one way, maybe doesn't. We're not thinking of that. We're really thinking of these are normal digital circuits. We're just going to interpret the inputs and outputs a little bit differently. So our work is the first to look at this synthesis of functions onto this sort of unconventional stochastic computing with this idea of approximation. So I want to leave you with a couple of thoughts here. One, think of this logic design as probability inputs, probabilistic outputs. So values that change. They're not exact. They're approximate. I get very good error tolerance. I can tolerate very high errors and still get good results, although the result is not exactly the same as the other perfect result. The hardware cost is very low. It has very good area delay product, especially for very complex operations. It's useful in applications where I can't tolerate large errors, but I can tolerate a little bit of constant error. Something like image processing, control systems, things where I have some compensation built in, for instance. And for all the nerds in us, there's a lot of fun math in this, so that's what we really enjoy. So with that, thank you very much for your attention.